DDC controllers, direct digital control controllers, bit of a mouthful. It references the fact that microprocessors can only control using binary switching in the same way that a computer does. This used to be an issue when I first started doing BeMS because of the resolution of binary switching. It's really not anymore. But it is important to understand that these are computers. So when we're performing our mathematical functions, we're looking at binary values. If any of you out there are BeMS engineers and you've dealt with Modbus, then you will know that understanding binary is extremely important to making these systems work. So because these days we have such powerful processors, we don't really need to worry too much about the BeMS in terms of what we do with DDC. So we can think of all of our values within BeMS as one of two types. They're either analog, which means it's a real value. So 0, 32, 74, 365.347, all real values, or digital values. And digital values are sometimes referred to as true or false, on or off. They have one of two values, either a 1 or a 0. So analog values, anything within a given range, digital values, on or off. The way that a BeMS controller is set up is it executes a program which is written by the engineer. And as I said, this is an overview. I'm not going to teach you how to write software here. But in order for a program to execute, you need input, you need to process that input, and you need to provide output. And in the case of our BeMS, our input for our program is taken in the forms of physical controller variables. That is the real world values that we connect into our system. And if you look at the little graphic there, we see that we have our software application running, and we've got these 5 variables being pulled into the system. We process those, and from the application that we're running, whatever that is, we can enable pumps, fans, speed control for pumps and fans, and we can modulate valve and damper actuators as well. This is the mainstay of any computer program. If you are operating a computer program on your desktop computer, it receives input, typically from your keyboard. It processes that input and it provides you with output. So if you're using Word, you press the W key, then the word processor sees the W key is pressed, and it looks at what font you're using, what size that font is, and it displays it on the screen. So that's a software application. Ours is no different. We look at the temperature, we probably compare it against a set point, and we perform a control action based on that. And that is all DDC controllers are doing. So in terms of the I/O that we have for our BeMS, we have analog inputs. Any controllers that have terminals designated as analog inputs will accept a varying signal from a sensor. And when I say a sensor, that's anything which is sensing an analog value out in the real world. For BeMS, we typically have 3 values that we look at. There are more, but the 3 here are the most common types of values that we see in BeMS in terms of analog signals. The first one is a varying resistance. If you have a resistor, if you think of a dimmer light switch, then what you're doing as you turn that dimmer is you're increasing or decreasing the resistance to the electrical signal going through, and so your light becomes brighter or dimmer. Have a similar system here. It's a much lower voltage, but basically if we vary the resistance of an electrical signal through a wire, then we can measure that variance in resistance and we can get a reading from it. And the other one is a change in voltage. We can use 0 to 10 volt DC signals. So we can measure anything out in the real world and transpose that to a voltage. Give you an example of that. Down the bottom there, 0 to 10 volt DC may represent 0 to 100% RH, which is relative humidity. So at 0 volts, we have no relative humidity. At 10 volts, we have 100% relative humidity. And obviously 5 volts DC, we would have 50% relative humidity. The other signal we use is a 4 to 20 milliamp signal. You also get 0 to 20 milliamp, but 4 to 20 milliamp is much more common. In the same way as a 0 to 10 volt DC signal, a 4 to 20 milliamp, at 4 milliamps, we might have 0% RH, and 20 milliamps, we might have 100% RH. And obviously everything incrementally between those will be on that sliding scale of 0 to 100. 4 to 20 milliamp offers a couple of advantages over 0 to 10 volt DC. You can often run 4 to 20 milliamps using 2 wires. Again, I won't go into the details of that, but it also has inherent error checking in it as well. If your current dips below 4 milliamps, then you know you've likely got a problem with your sensor. It's also not susceptible to voltage drop in the same way as 0 to 10 volts DC. But these three methods are very typical ways of getting our analog values into our controllers. Digital inputs. If you have terminals on your controller designated as a digital input, then they're designed to accept one of two states, on or off. As I've said in an earlier slide, binary inputs are sometimes referred to as on, off, true, false, 1, 0, high, low, but effectively they're the same thing. It's either on or it's off. It only has two states. A very typical example of a digital input would be the status of an airflow switch. It shows on when the fan is running and off when the fan is stopped. There's no other states. It's either on or it's off. And we can use digital inputs for lots of different things within our building management system. As well as analog and digital inputs, we have analog and digital outputs on our controllers as well. Analog outputs will give a varying output, usually in the form of a 0 to 10 volt signal. Some earlier controllers, which were sort of took their lead from process control, used 4 to 20 milliamp signals. That is very uncommon to find a 4 to 20 milliamp output on your BeMS controller now. They are almost all 0 to 10 volt analog outputs. What we can do with that 0 to 10 volt signal is to drive an actuator to a position. So if you can think of a valve that's opening and closing, and we need to position that valve somewhere within its range, we can give it a voltage from 0 to 10 volts DC to say whether it needs to be at 0% or 100% or at any point in between. Now, it's important to understand that we don't use the 0 to 10 volt signal to actually drive the actuator itself. The actuator will get power, usually 24 volts DC or 240 volts DC sometimes. That 0 to 10 volts DC is just a signal to tell it where to position itself. And we use analog outputs for a number of different reasons. Very typically, it's for valves and dampers to position them, but we also need to do things, for example, with variable speed drives. A variable speed drive varies the speed of a fan or a pump, and we need to tell it what speed to go. So we would give it a 0 to 10 volt DC signal, and that would set the speed of that fan. So they're the opposite of an analog input. We have an analog output, but like I say, very, very common is 0 to 10 volt DC. Can't think off the top of my head of any modern controllers that don't have 0 to 10 volt DC outputs. We also have digital outputs. If you have controllers with digital outputs, then they will either be on or they will be off. And obviously we use this for switching plant on and off, boilers, pumps, fans, whatever it is. We switch them on and off using a digital output. The way the digital outputs are configured does actually tend to vary considerably depending on the types of controllers you've got. Some of them have volt-free digital outputs. That means it's a relay the relay clicks in, which means that whatever you connect to it has to supply the voltage. The relay itself is free of any voltage. You need to be careful when you're using these because some will switch mains voltage, some will switch not, but this is down to the individual manufacturers. So it's very important to read the instructions, or else you could potentially set fire to ASDAs in Clapham. I'm just saying, just putting that out there. Other controllers don't have volt free. What they have is an active output. So it may put 24 volts out of the controller, which you can then use to switch a relay. Some of them have what are known as wet contacts or active contacts, so that you can you can set up a separate circuit to actually activate the digital output. But they all perform the same function. They either have a status of on or off, and they're used for enabling and disabling the plant. In addition to the physical I/O, we also need to have software data points within our system. Software data points are accessible to anyone who's engineering it, but it's also, these are some of the points that we use when we're engineering a head-end system. For example, a set point needs to exist within the system. If you are controlling the temperature in a room, you want to control that temperature at 22 degrees C. Where do you set that? Now, you might have a set point on the sensor itself, or more likely, that will be programmed into the controller. So we have software data points to do that. Software data points can either be analog or digital. Now, the big difference with software data points is it very much depends on whose system you're using as to how you implement software data points and how they work. So some people just have very simply analog and digital data points. Trend, for example, have a number of different varieties. If you want to use a set point with a trend controller, for example, then you engineer what is known as a knob module, which is akin to a knob that you turn, and a digital set point is a switch. So there's different ways of doing this, but essentially they're the same thing. The controller application itself, the controller application provides all of the necessary functionality. It's no good just connecting a whole bunch of sensors up to a DDC controller and a load of actuators on the output side. It won't do anything. You need a brilliant BeMS engineer to do this for you. We like to think it's dark magic. It's really not. It's just connecting a whole bunch of lines together. These drawings here, or the diagram you've got here, is actually part of a trend controller application. The one on the left, this is what is known as a sensor type module. When we bring in a signal into a trend controller, we have to tell it what type of sensor it is. So we have to define that within the software. The one on the left is a loop module, where we define the proportional, integral, and derivative action for our control loops. So I'm not going to dwell on what they are. That's not really what this course is about. But you typically put the function blocks onto the page, and then you join them together with wires to create the software application. That's a very typical way of doing this. When I first started doing this, as I say, it was the early 90s when I transitioned to doing BeMS control. You had to write the software by hand, which meant sitting down and actually typing in all of the code, which would effectively provide you with these software applications. But thankfully, we don't need to do that anymore. On this next slide, just showing you a controller application. This doesn't do very much, but it does illustrate the point. Now, the previous slide, we had the trend software. This is taken from the EasyIO software, which is a programming language which is called Sedona. And it shows a set of blocks. If you look at the diagram, you'll see there's the const fl and the const f1. Those are constants. So those are analog values which are defined in the software. So you just drop those onto the page. And then I've given one a value of 3 and the other one a value of 2. We then drop an add to block onto the page, and the purpose of an add to block is to add two numbers together. And if you look at the diagram, I've drawn lines between the two, and you literally just draw those lines in the software, and it will take in one and in two, it will add them together. And where it says out, we have a value of 5, which is obviously 2 and 3, which we could then use elsewhere in the software. And that is how you build up the software. If you don't actually work with software, but you've seen the software, you'll see it is a lot more complex than that. There's a lot more blocks on the page, but this is what we're doing, and this is how we follow the software through in our BeMS controllers. This is a more common controller application. What we've done here is we've defined a variable temperature circuit and an outside air temperature rescheduling set point. And again, it's just a diagram to illustrate the point. Although this is overly simplistic, this is a fully functioning piece of software. It looks at the outside air temperature. It creates a flow temperature set point based on the outside air temperature. We then look at the variable temperature flow or the variable flow temperature itself. We compare that with the set point that we've calculated, and we position a valve to try and maintain that flow temperature where it needs to be. There's loads of different ways of doing this. Some systems require you to build your control application and then you compile it and you download it. Some systems allow you to program it live. In the case of that Sedona application that we saw on the previous slide, you program that live into the controller. With Trend, which this is Trend software you're looking at now, in Trend software, you can pre-program it and then download it, or you can actually work live on the application. So there's lots of different ways to do this, and it depends on the type of controller and the manufacturer of that controller as to how we do that.